All right, so here we go. 5.8. So a local maximum is basically oh, come on. The y-coordinate of the point higher than its surrounding points. Its surrounding NDING points. All right, so the y-coordinate of the point higher than its surrounding point. So for example, if I had a graph that looks like this, that kind of goes woo, whoop. All right, this right here would be a local maximum. Okay, it's not the maximum. Does this graph even have a maximum? No, it goes up forever. So there is no maximum, but it has a localized maximum. This is actually called, the more technical term for it is a local extrema. All right, is probably, if you ever get to calculus, that's the term they're going to use. They're going to use the term extrema. Basically, where are the maximums and minimums? I don't know if that's Latin or what, but that's just I think we use that word so we sound smart. I don't know. I have no idea. But that's the local maximum. It's a local extrema. A local minimum. Same thing. Except lower than surrounding points. SO, surrounding points. All right, and so in this case, that would be a local minimum. All right, so you got a local maximum, you got a local minimum. Okay? Cool? Any questions so far? Are we making up for beating each other on the football field yesterday? All right, whatever. All right, even function. Even function basically is a function whose highest exponent, aka the degree is even. For example, x to the 8th plus x to the 7th plus x to the 3rd plus 2 would be an even function. Even though everything else is odd, the highest exponent is even. That's an even function. An odd function, same thing. Same, except degree is odd. Degree is odd. Not off, odd. So like x to the 9th plus x to the 4th plus x squared minus 2. All right, because the biggest exponent is odd, that would be an odd function. All right, so the biggest reason they distinguish between these two is even functions tend to do the same types of things on graphs, and odd functions tend to do the same things on graphs. So like even functions, they tend up going both the same direction. Like they both go up and they both go down, kind of like touchdown, or I have no idea what 2 arms down would be in football or any other sport. They've been like, I don't know, whatever. But like they both go the same direction, versus an odd function be like, I walk like an Egyptian, walk like an Egyptian. It's pretty odd to look at, especially Mr. Hunter doing that. Yeah, whatever. All right, so an even function, your graph is both gonna go the same direction. An odd function, no matter how many turns there are or how many extrema, they're gonna go in different directions. That's one of the differences. Okay, but we're gonna talk a little bit about those today. All right, any questions about this so far? If you're still riding, try to finish up here in about 10, 15 seconds. All right, here we go. Next page. I'm actually going to skip this page. We're going to this page. All right. It says find all the zeros of the polynomial function. Find all the zeros of the polynomial function. We just had a test on factoring, right? Yeah, we're done factoring for a while. No, we are going to come back to it. We're going to use it. But hey, if it just says find the solutions, I don't care how you do it. Unless you're retaking the factoring test, then you probably should factor. But that's beside the point. So find all the zeros. So take out your calculator. Take out a calculator. Here we go. Go to y equals. Clear the old one out. And you're right over there. And plug in your function. Conjunction, junction, what's your function? So we got 6x to the third. Where's my mouse? Okay, 6x to the third. No. Plus 5x squared. Plus 5x squared. Minus 17x. What? Minus 17x. Minus 6. All right, cool. So that's the function they gave us. All right, I'm going to go to the table. All right, if I go to the table, can you tell right off the bat where one of the solutions are? -2. Good. That's where. Why is that? Why do you know that's a solution? Because y is 0. Exactly. All right. So we're going to go ahead and write that down. X equals -2. That's one of your answers. Okay. Question. I'm going to tell you that the next answer is somewhere between -1 and 0. Why would I tell you that the answer is somewhere between those 2 points? What on the chart would tell me there's a solution somewhere in there? The 10 and the -6. Why would that be a big clue? Because it jumps to a negative. 10. Is 10 above the x-axis or below the x-axis? It's above. -6. Is that above or below? Below. So it went from above to below. Do you think it crossed the x-axis?
Yeah.
Yeah, exactly. So basically, here's what I'm saying. 10. 10 is up here somewhere. All right, -6 down here somewhere. So the graph went, it crossed the x-axis somewhere between -1 and 0. Cool. So I can tell from the chart, there's a solution between those 2 points. Okay, where else might there be a solution? 12 and 28. So my x values are 1 and 2 because the sign changed over there. The sign changed, therefore it crossed the x-axis. Cool. Sweet. So here we go. Let's talk about how to find those real fast. Erase, 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 erase. Good. All right. So for this, we're actually going to have to look at the graph. And the graph goes, sweet. All right. So we know the -2. We need to learn this one first. So here's what we're going to do. We're going to do a second trace. And actually, there's a calc. Calc stands for calculate up there. So second calculate. And now, which one of these do you think would help us to find a solution? 0! Because they're also called zeros. So you can either scroll down to it or hit 2. Cool? You okay over there? All right, so if we're finding this, it's going to ask us for a left bound and a right bound. So I'm going to pick a left bound, let's say -1. And I'll tell you why in a second. Enter. And we're going to pick a right bound. I'm going to pick a right bound let's pick a right bound of +1. All right, now yours doesn't do the little dotted lines, but you see how there's a dotted line on the left and the right? Here's why we did this. Your calculator can do a lot of things, but in essence, your calculator is very stupid. Okay? All right. It doesn't realize that if I say find the solution here, it knows the function goes forever to the left and forever to the right. So it will go forever to the left until it gets so small or the number gets so crazy that it poops itself and stops. Literally, that's what it'll do. You follow me? So you have to give it a range so that it knows where to look. The other thing is, you notice how there are 3 solutions right here? If you don't narrow it down to the range where one of them is, it will go, well, which one do you want? And so it will either pick one, and it might be the one you want, or again, it'll go, too many inputs and poop itself and stop. You follow me? One of 2 things will happen. No. So here we go. That's why I gave it that range. I have to give it a left side and a right side so it knows where to look. And then it says guess. I have no idea why it says guess next. It has done that since the original programming back in the 80s. All right? Hit enter again, and that's your 0. Negative 0.333333333, which, what's that as a fraction? 1/3. Good. So that's negative 1/3, comma 0. Cool? That's that 0. So we got negative 2, negative 1/3, and let's do this one. Okay? Second, calculate. Which one are we using again? 0, so 2. And we're going to do this one right here. So what's a point to the left? 1. 1 is to the left, so we can choose 1. What would be a point to the right? 2. 2 would work, 3 would work, 4 would work. Anything to the right would work, but 2 is fine. So we narrow it down to that. And so the calculator goes, dun, dun, oh, 1.5, 0. Or you can do 3 halves, 0. So here we go. Your answers are, let's use a different color. X, come on, stop it. X equals negative 2, negative 1/2, and 1.5. Those are your solutions. Negative 2, negative 1/2, and 1.5. Okay? That makes sense? Let's do letter B real quick. Make sure we're all on the same page. All right? Letter B. Same idea. Go back to your calculator. What's the first thing we're going to do with the calculator? Plug it in. All right, so y equals, clear the old one out. We got 4x to the third. Okay, 4x to the third. How many solutions would there be to a 4x to the third? 3, or a maximum of 3. There could be less, but there's well, imaginaries as well, but there are 3 solutions one way or another. Plus 28x squared plus 21x minus 81. And let's hit graph. Sweet. All right, so that's where they are. I'll look at the table, actually, because it might give us one right off the bat. Does it give us one right off the bat? Negative 3, good. We don't have to calculate that one. It's right there for us. All right, so let's go to the graph and calculate the next 2. So let's start with the left one. What do I do to find that left one? Walk me through it. Second what? Calculate, or second trace, however you want to think of that. Which one do we choose? The second one, 0. Okay. Left bound. What's something to the left? Negative 6 or negative 7. That's fine. Negative 6. We'll choose negative 6. What would be something to the right? Negative 5. Or we could use negative 4. If you weren't totally sure about the negative 5. Now question, why would negative 1 be a bad idea? Good, there would be 2 solutions in there. So negative 1 is a bad idea. Hello.
I have no stuff. Did anyone drop off stuff for me?
No one dropped off stuff for you, Maria. I'm sorry. Do you need to go find it?
Yes, I do.
All right, here we go. So negative 4, enter. So we got it down. There's only one between them. It says guess, don't know why. So negative 5.3 and then 1e negative 11. Does anybody know what 1e negative 11 means? Good! This is the first class today to know what that meant. That is 1 times 10 to the negative 11th. Which, is that a really big number or a really small number? That's tiny. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Which, for all practical purposes, that number is what? 0. It is essentially 0. All right. The calculator, because of the way it calculates this, sometimes it doesn't always land on 0. But that's close enough that you know this is 0. So if you see an E, a capital E, that's the calculator's way of saying scientific notation, times 10 to the power of that. Cool? So let me erase that. Try again. There we go. All right. So we got negative 5.30. Let's do the right one. All right, how do we find the one to the right? Walk me through it. Second trace. Then what? 0. Okay, what am I going to put in first? Negative 1, that would work, because that's to the left of it. Okay, then it says right bound. 2, okay, 2 is to the right of it. That works. Cool. And that's your right, that's your other one. What you got?
It doesn't say right bound.
Okay, it says guess. Hit enter one more time. There it is, negative 30.
So
That's one of them. That's that one right there that's highlighted. Okay, so I got 1 point through 0. So here we go. Let's go back. Your answers are x. Oh my goodness, forgot to do that every single time. X equals negative 5.2. We got negative 3, and we got positive 1.3. Was that it? Yay! Those are your solutions. You okay? How are we doing this? Give me a 5 to 1. 5, I got this. 4 I'm okay. 3 and 2 I'm lost. Save. Sweet. Are you pushing the buttons with us, Dan? All right, switch page. Go to the next page. This one piles on a little bit. So it says graph the function. That's the easy part. Then it says identify all local maximums and minimums and state the intervals where the function is increasing and decreasing. All right, this is one of those things that's easier than it looks, or easier than it sounds, okay? So we're going to start off by straight up sticking it in the calculator, okay? So here we go. Woohoo! Use the calculator. Go to y equals. Put it in. What was it? X to the third minus 3x squared. X to the third minus 3x squared. Minus 3x squared plus 6. Minus 3x squared. Is it plus 6? Not 6, it's just plus 6. Cool. Alright, graph. So it's a cube, so there are 3 solutions, but how many real solutions are there? 1. There's only 1 real solution. The other 2 are imaginary, and they're probably up here somewhere. You don't have to know that, but they are imaginary. So let's find this one. How do we find this 0? Second trace. 0. Okay, pick something to the left. Negative 4. Sounds great. Pick something to the right. 1. Sounds great. We had a lot more leeway with this one. Even though it's the only one, you still got to give it a range. All right, so it says guess. Hit enter, and we get negative 1.20. Cool? Yes, sir. Sure. Negative 1.20. So we can go back to our graph. And we know that we have a 0, negative 1.20. That is a 0. And I can go ahead and graph it. Negative 1.2. Right there. That's my 0. Cool? All right. The instructions say also find the local maximums and minimums. All right, so for this one, let's go to our calculator. This one's a little bit trickier, but not by a whole lot. We're going to go to second calculate, but for this one right here, do you think that one's a maximum or a minimum? Maximum. So which one do you think we're going to use? 4. I knew y'all could catch on to this. All right, and then it asks for a left bound and right bound again. All right, so this one's a little trickier because you got to be a little more specific. If I pick something to the left, I want something like, so let's do negative 2. That's to the left of it. But to the right, if I pick something like 5 over here, it's going to pick something like this as the maximum. Because it's going to find the highest point in the range that I give it. Does that make sense? And if I give this as my right side, it's going to pick that point right there. So I need to make sure I zero this in a little bit better. So what if I pick x is 2? All right? That's between those two. And now that is for sure the highest point. You follow me? So it will find the highest point. So you need to make sure that the one you want is actually the highest point in there. Cool? Then it says guess. Hit enter. So the maximum is at what? 1.05 e negative 6. So the x value is essentially what? This was essentially 0. E to the negative 6, that's 5 zeros and then a 1. That's pretty stinking small. All right? So your y value is 6. So again, I'll go back over here. I've got a max. Gotta remember to do that. A max at 0, 6. Cool, which is right 1, 2, 3, 4, 5, 6, right there. Cool. So I got a 0, I got a max, and then they also ask for minimums. Is there a local minimum on this graph? Yes! How do you think we're going to find it? Second, trace. What are we going to pick? 3. Pick something to the left. What do you want to pick for it? 1. Okay, that's a good one. Pick something to the right for the right bound. What are you going to pick? 3. Okay, let's see. Yeah, that's good. And what do you get?
2.
Essentially 2. 2. Yeah, 1.99999. Yeah, that's a 2 for all practical purposes. So we got a point, a minimum. Oh, stupid machine. I got a minimum at 2, 2, which is right here. So this graph, see if I can draw it like this, goes like that. Huh? Did I do 2, 1? This is why I keep you around, Anthony. Keep me humble. This is the only reason. You're absolutely right. So there we go. There's that. And let's pick that one. Oh, I wish I were an Oscar Mayer wiener. There we go. And so that's your graph. Cool? Any questions on how we did this? Any problems? You look like you're struggling with me now. All right, we'll talk. We're going to finish up here in just a second. We'll get it. Here's the last thing it asks. It asks for where is it increasing and decreasing? Which increasing is a fancy word for going which way? Up. Yeah, I know. Decreasing is a fancy word for going down. I know. So here we go. Let's pick, what color we want? Green. Sounds good. So question. As I walk, if I'm walking from left to right, this side of the graph over here, am I walking uphill or am I walking downhill?
Down.
Well, this graph is going up until that point right there. What is the x value right here? 0. It's at 0, 6. So the x value is 0. So I am increasing from negative infinity to 0. So basically everything to the left of 0, the graph is going up. All right? Let's zoom in a little bit. All right, from that point, we're right here again. Remember, we're right here at 0. It turns around. Does it keep going up or does it start going down? It goes down. Where does it stop going down? At 2, when x is 2. So it's decreasing from 0 to 2. All right, so as you walk from the x is 0 to the x is 2, it's going down. All right, at that point, do we keep going down forever, or do we turn back around and start going up? We start going up. From 0 to what point? Infinity. So from 0 to infinity, going up again. Those are the ranges where it is increasing or decreasing, or the domains, I should say. All right? Here's another way of thinking of it. We're grabbing the x values, right? So if I grab, let's do, come off it. Come on. There we go. Helps if I pick the right one. Ooh, purple. So if I go from here, this is where I stop going up. From negative infinity to that point, it stops going up. From here to that point, it's going where? Up or down? Down. So that range is going down from 0 to 2. And from here to infinity, which way is it going, up or down? Up. The graph is going up. All right, that's what it's asking you for, is where is it going up and down? All right? And I'm actually going to stop right there, because I think you can do this, unless you really want another example. I don't think so either. This stuff bores the crap out of me too. All right? Sorry, done.